Alright, the next thing we're going to look at is rationalizing denominators. And this is the process of writing an expression as an equivalent expression, but without a radical in the denominator. So somewhere along the way in math, someone decided that we don't consider an expression with radical simplified if there is a radical in the denominator. So anytime we have a radical in the denominator, then we're going to need to do this rationalization process. And what we're looking to do is what I mentioned earlier in the video, is what makes a root lift or go away is when we know how to evaluate it. So by creating a perfect square, cube, whatever it is we need, it will remove a radical. So for an example, if I multiply square root of 2 times square root of 2, that's square root of 2 times 2, which is square root of 4. You see that created a perfect square. So we can evaluate that and make it a 2, and the radical is gone. So as we look through these examples, this is what we're going to be looking to do. For the first one, I have 2 over the square root of 7. So having that root in the denominator is not okay. So what we want to do is to force a complete square, a perfect square, so that we can evaluate it. Now it turns out that square roots are easier than cube. If I have the square root of 7 in the denominator, I just need to multiply times the square root of 7 to make that a perfect square. But of course, we can't just multiply the denominator by something. If we multiply the denominator, we also have to multiply the numerator so that we're really multiplying by a factor of 1. Alright, so in the top, we have 2 times root 7 over, in the bottom, we have 2 radicals with the same index, so we can write them together. So we have 2 root 7 on the top over the square root of 49. And then we have created a perfect square under the radical in the denominator. So we know that the square root of 49 is 7. So this is my final answer. And again, yes, I do want to see the steps because this is the process that I'm going to be assessing. Okay? All right, for number 2, it doesn't matter that there's a radical in the top. What we're concerned about is the one in the bottom. So since we have the square root of 3, we create a perfect square by multiplying by another square root of 3. And then we have to also do it in the top so that we're creating an equivalent expression. So in the top, I have the square root of 5 times 3. And in the bottom, the square root of 3 times 3. And then if I simplify, in the top, that's the square root of 15. The bottom is square root of 9. And that leaves me with square root of 15 over square root of 9. That's a perfect square, so we know that that is 3. Now when it's a cube root, it's a little more difficult. So first I'm going to work it wrong to show you. So if we use the same idea that we've been doing, say, well, I see a cube root of 2 in the bottom. So I'm just going to multiply by cube root of 2. to rationalize. If I did that, we'd get 5 times the cube root of 2 over. In the bottom is the cube root of 2 times 2. And we get 5 cube root of 2 over the cube root of 4. Well, the problem is 4 is not a perfect cube. So my root is not going to go away. I'm still going to have a radical in the bottom. So what we have to do when it's not a square root is instead think about how many more we're going to need. So I have the cube root of 2. Well, we know a perfect cube is something times itself 3 times. So the cube root of 2, we have 1, 2. To make it a perfect cube, we're actually going to need 2 more. Now, if you want to write that as cube root of 4, that is also fine. I'm just trying to illustrate there that this is 2 to the first, so we need 2 to the second to give me 2 times 2 times 2, which is the perfect cube. Okay? So in the top, we're just going to have 5 times the cube root of 4. And on the bottom, we'll have cube root of 2 times 4 now. So we get cube root of 8, which is now a perfect cube. So we know that the cube root of 8 is 2. And that would be my final answer. All right, a couple more of these. So number 4, that one is actually pretty similar. It's just that we have a number out front. I have the square root of 5 in the bottom. So I need 1 more to make a perfect square. And we also have to do it in the top. So we have 2 times root 3 times root 5 over square root of 5 times 5. Of course, in the top, we can write that as 3 times 5. And then that's 2 times the square root of 15. And now in the bottom, we have the square root of 25, which is 5. All right? For number 5, let's go ahead and do what we did with the division problems and split the problem. So now I have a radical in the denominator. It is a square root, so that means we basically just need 1 copy of what's in the bottom. So in the top, we're going to get the square root of 3x times 5y. And in the bottom, we're going to get the square root of 5y times 5y. So in the top, we get the square root 3 times 5 is 15xy. And the bottom, the square root 5 times 5 is 25. Y times y is y squared. So we can't really do anything with the one in the top. But 25y squared, those are both perfect squares, right? So remember, if you want to do it this way, then we know that index and root will cancel, and I'm going to have a 5y left in the bottom.